In part 12 of this series, I focused on the requirements for a good precipitate and the issues regarding contamination. It was the starting point for gravimetric analysis. This presentation will be focused on the principles behind the derived values and how they are actually calculated in practice. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. I have stated many times throughout the series, locate and download a good periodic table. Almost all gravimetric calculations are based on the values listed in this table of elements. The atomic mass and the ion charge are the most important. Ion charges allow for the determination of products from chemical reactions, among other requirements. Mass weights allow for the concentration of analysis of species within compounds, which in turn allows for the statistical assay of minerals within your mining claim or area of prospect. The atomic weight of an element is abbreviated as AT, whereas the atomic weight of a compound is abbreviated as WT. Ion charges are listed as shown. Using the example of copper-2 chloride, since chlorine has a single charge of 1- and copper has a charge of 2+, there must be 2 chlorine atoms combined with 1 copper atom to make a compound or molecule of copper-2 chloride. Note that there are 2 ion charges listed for copper. The copper with the ion charge of 2+ is the most common and is named as copper-2 or a copper-2 atom or ion. The top listed values in the table are the most common species of that element. The copper atom may also have a copper-1 charge, and therefore, even though less common, has the name of copper-1. There is also a copper without an ion charge. Now those elements will be discussed in a future presentation in this series. Now matter can neither be created nor destroyed, only changed. In any equation, there are reactants and there are products. The arrow in the equation is the reaction point. The reactants are always on the left and the products on the right. The product side will contain the same number of atoms as there are reactants. This has been shown many times throughout this series. In any formula or equation, the equation must be balanced. Equal number of atoms per side. 2 chlorine atoms in the reactant side of the copper-2 chloride reaction, and 2 chlorine atoms in the product side. In order to find the molecular weight or mole weight of a compound or molecule, one simply adds up the weight of each atom in the formula for that molecule. Copper-2 chloride contains 1 atom of copper with an atomic weight of 63.5 grams and 2 atoms of chlorine having atomic weights of 35.5 grams. The total molecular weight of the compound is therefore 134 grams per mole. To calculate the results of an analytical analysis, there are 2 measurements that are primarily used. The first is the weight of the sample, and the other is the weight of the product, which is the analyte. The mathematical equation is quite simple. It is the weight of the analyte, that is the element of interest, divided by the molecular or mole weight of the molecule, then multiplied by 100 to give us percentage. Using the example compound from the previous slide, the percentage of copper-2 ion in the compound of copper-2 chloride would equate to 63.5 grams per mole of the copper divided by 134.5 grams per mole of the copper-2 chloride, multiplied by 100 to give us the percentage of the copper ion, which is 47.2% copper-2. The percentage would be the same, regardless of the amount or mass weight of the pure sample. The scale in the picture shows a weight of 0.180 grams of precipitate. The total percentage of the copper-2 would be 47.2% of that weight. This can be taken a step further. Now the gram weight of the copper-2 in this mass of copper-2 chloride precipitate would be the 0.180 grams multiplied by the 47.2%, or 0.0180 times 0.472, which equates to 8.50 milligrams. Now, why is this calculation important? Well, if you wanted to create a solution of copper 2 chloride, you would need to know the mole weight of the copper that would be in solution. 8.50 milligrams equates to 0.008496, which is rounded off to 0.00850, divided by the 63.5 grams per mole of copper, which would give us 1.34 times 10 to the fourth moles of copper 2 ion. From that figure, the molarity of your solution can be calculated. When the product that needs to be analyzed is not the analyte itself, which normally would be the element of interest such as copper 2, silver, or uranium-6, a gravimetric factor will need to be used to correspond to the percent A, that is, the analyte. The gravimetric factor, or number used, is equal to the number of moles, or atoms, of the critical substance that you are looking for, divided by the number of moles or atoms of the substance weighed. This is then multiplied by the mole weight of the substance sought, which is divided by the mole weight of the substance weighed. The substance weighed is the sample weight. A and B are whole numbers, which is based on the molecular formula of the sample. A is the number of moles or atoms of the weighed substance, which is the sample, and B is the number of atoms in the substance that you are looking for. The gravimetric factor calculation is not that confusing. In these examples, uranium-6 is the element of interest. Uranite is uranium-6 dioxide, or simply uranium dioxide. As the analyte of interest is only uranium, the gravimetric factor calculation is the same as that for the percentage of analyte, percent A. The difference is that we do not multiply the resulting value by 100 to obtain a percentage. In fact, each one of these results can be multiplied by 100 to obtain a percentage. But the resulting values for these calculations, that is the gravimetric factor, is used to calculate the weight of the species sought, whether it is the compound or the element of interest. Now, looking at bornite. For bornite, one might be interested in the copper weight, or the weight of the iron content, or maybe just the weight of the iron sulfide in the ore. When needing to know what the concentration of a compound may be, the gravimetric factor is the mathematical tool to use. Sulfur, for example, is used in the making of sulfuric acid. If we measured 0.3345 grams of sulfur, how much sulfuric acid could be made? And what would the concentration of the solution be? Well, the product, which is the sulfuric acid in this case, and the measured weight of the sample, being the sulfur, the gravimetric factor will be the mass weight of the product divided by the mole weight of the sulfur, in this case, the sample. Since there is only 1 mole of sulfuric acid having an atomic mass weight of 98.1 grams per mole, it is divided by 1 mole of the sulfur, which has an atomic weight of 32.1 grams per mole. The gravimetric factor in this case is 3.056. The weight of the sample measured is 0.3345 grams. Multiplying 3.056 by 0.3345 gives us a product weight of 1.022 grams of sulfuric acid, theoretically. We now have the weight of the product, and we have the weight of the sample. The percentage, A%, is equal to 0.3345 grams of weighed sample divided by the product weight calculated as 1.022 grams multiplied by 100 gives us a concentration of 32.70% weight to weight. Knowing these values, the volume of solution can now be calculated. The picture shown represents a conversion of one species to another. It is only a representation. However, the concentration of a species may need to be known. There are many times that a sample will need to be converted to something else to be able to obtain a gravimetric factor. The barium sulfate will be the case example. To determine the gravimetric factor for the conversion of sulfur, the sulfur content of this compound will need to be converted. In accordance to the solubility rules, an iron 3 chloride solution is chosen. The product produced is iron 3 sulfide. What has been completed is the conversion of the barium compound to that of a solid iron compound. As noted in the previous slide, any calculation must be balanced, and it must be stoichiometric. The gravimetric factor is based on the product divided by the sample. Now take note that there is 1 atom of sulfur in the barium sulfate and 3 atoms of sulfur in the iron 3 sulfide. This allows for the creation of a simple stoichiometric equation as shown, and allows for the cancelling out of the species to give us the remaining values. Since the conversion is between the barium sulfate and the iron 3 sulfide, the only species of interest for this calculation is the sulfur that we want as the G factor to be used for the barium compound and the iron 3 compound. The atomic and mass weight for these 3 species is shown. Therefore, the gravimetric factor is therefore equal to the 1 mole of sulfur multiplied by the 207.9 grams of iron 3 sulfide, divided by 3 moles of sulfur times 233.4 grams of barium sulfate. The gravimetric factor is thus 0.2967. So far, I have, in the last few slides, focused on the element of interest. Well, it's not just the element of interest. It can also be molecules or compounds of interest. In nature, hematite is converted to chromite by geological forces. This can also be duplicated in the laboratory. The equations are shown. Hematite is converted to chromate. The product, therefore, is iron chromate, and the sample is iron oxide. Therefore, the gravimetric factor will be the 2 moles of the iron oxide divided by the 1 mole of the iron chromate, multiplied by the mass molecular weight of the product, divided by the mass molecular weight of the sample. Therefore, the formula is balanced in regards to the critical element, which is iron, and is stoichiometric. The metallic element is the critical element, as it is the element found in the product and in the sample. The chromium oxide ion is not listed as an ion in the product. It is the reactant, nor is the chromate ion listed in the sample. The mass atomic weights of both compounds are shown, as it is the compound of interest that is required. The atomic weight of the critical element is not. However, its molar abundance, or number of moles, for the sample and the product is required for the gravimetric calculation. The G factor in this case is 2.804. For small-scale miners, prospectors, and hobbyists that conduct their own experiments at times, their biggest question is, how big should my sample be for chemical analysis? Well, the gravimetric factor is the tool to use to answer this important question. Presented here is a real-life example using a rare metallic ore known as schreibersite, a mineral deposited by hydrothermal mineral-rich fluids. This rare mineral ore is a natural alloy, referred to as a ferroalloy, as it is rich in iron. The formula is shown as 3 parts iron and nickel together and 1 part phosphorus. Constituently, it is roughly 63% iron, 22% nickel, and 15% phosphorus. The atomic weights are shown for each element. The mass weight of the ferroalloy is also shown. In most cases, the mass of the precipitate that is easy to handle or manipulate is roughly 175 milligrams or 0.175 grams. The question now is how much sample mass is needed for a 175 milligram nickel precipitate. Well, the gravimetric factor is thus based on the nickel. Since the nickel is the product, the schreibersite becomes the sample. and thus the atomic weight of the nickel divided by the mass weight of the sample equates to 0.1567. This is the gravimetric factor. The nickel at 22% in decimal form is 0.22, which, divided by the gravimetric factor of 0.1567, the value obtained is 1.404. Now the required weight of the precipitate is 175 milligrams, or 0.175 grams. Dividing the 0.175 grams by the 1.404, the result is 1.246, or a 1.246 gram sample. The answer in this case would be approximately 2, but not greater than, a 1.246 gram sample of schreibersite. In this presentation, I introduce the gravimetric factor, how it is calculated, and how it is used to determine the weight of a molecule or compound, but also the required weight of a sample that is easily manipulated, that is worked upon. I attempted to do so without a lot of theory, and I hope that I achieved this goal. If you found this presentation interesting, I hope that it will entice you to view Part 14 when it is published. And if you know of someone who may benefit from this presentation, please give it a like and a share. It's my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.